Hello, this is Jack Jackson. In this video, we're going to look at another type of continuous distribution that's actually used quite a bit in real-world problems, and it's called a t-distribution. So this is another family of distributions. In this video, we're going to be talking about the properties of the t-distributions, and then we'll have a follow-up video talking about their calculations with them. In fact, in the following two sections, we will actually apply techniques from our earlier sections to three types of families of distributions: t-distributions, chi-square distributions, and f-distributions, and along with the normal distributions. These are the four types that are typically used in inferential statistics. So we'll be using these in our fourth unit quite a bit. So in this unit, here's what we're going to do. We're going to use them extensively in our last unit on inferential statistics. In that fourth unit, we will discuss how they arise there, how they're used, do some real-world problems with them. In this unit, the only thing we're going to do right here in this section is how to use the basic ideas of the things that we've done so far to look at things like look at the graph of the PDF and the graph of the CDF and see what they look like. Look at the characteristics of those things, and that's basically this video for the t-distribution. And then we're going to calculate probabilities using the built-in CDF function in the calculator, and inverse probabilities using the CDF graph, and if available, a built-in inverse CDF. These things are all available on the newer version, at least, of the TI-84 and the Nspire calculators, so we'll be using those today. So first of all, t-distributions are actually a family of distributions, like normal distributions are a family. And just like the normal distributions, we identify which normal it is by identifying the mean and standard deviation. We identify each of the t-distributions by a parameter that's called the degrees of freedom. The degrees of freedom is a natural number, so it's 1, 2, 3, 4, whatever. And in the context of inferential statistics, we're going to be looking at some kind of a sample, and if you take one away from the sample size minus 1, that's going to be the degrees of freedom. But for right now, it's just a given parameter. I will tell you what that is. So one distribution for each degree of freedom value. Now, it turns out that these graphs are very close to the similar to the standard normal distribution. So the standard normal distribution PDF is going to be very similar to the t-PDF. The standard normal distribution CDF is going to be very close to the t PDF. Now the CDFs will be similar, the PDFs will be similar. So on the PDFs, remember the normal is a bell-shaped curve. The PDF on the t is also a bell-shaped curve. It's like the standard normal. The standard normal has mean 0. All the t-distributions, all the different degrees of freedom, they all have mean 0. So they have the same center as the standard normal distribution. The standard deviation in a standard normal distribution is 1. The standard deviations in all the t-distributions, they're a little bit larger than 1, but somewhat close to 1, but a little larger. And so that means because the mean is 0 and so forth, bell-shaped curve, they are symmetric about the mean, just like the standard normal is. As it turns out, the larger the degrees of freedom, the closer the distribution, the t-distribution is to a standard normal distribution. So let's look about how we could graph the t-distribution PDF on a TI-84. So if you hit distribution, which remember is second variables, you will notice that it will come up with a list of different distributions. If you remember, that's where we got our normal PDF, normal CDF, and inverse normal. But if you look right after those, 4, 5, and 6 are an inverse T, a T-PDF, and a T-CDF. So notice that we have all three of those available: an inverse norm, an inverse T, a T-PDF, and a T-CDF. That's sort of the ideal situation, is to have a CDF, a PDF, and an inverse all available. Now, some of the older TI-83 calculators, in particular, may not have the inverse T, and I'll show you a way to get around that if you don't have it. But if you do have it, it'll be a nice shortcut. So we'll use that. So now what we want to do here is just graph the PDF. So we just hit y equals, and in y1, we're going to put in TPDF of x, comma 5. So you just hit y1, hit distribution, second variables, choose number 5, and then put in x, comma 5. We can use a window pretty much the same as we would for a standard normal. So I'm going to go out from about -4 to 4 on this particular one. And I'm going to need y's. Well, I went a little below the x-axis to -0.1, and 0.4 puts you just barely above the top for a standard normal, and the t will be, about the same or just slightly under that. And there we go. We see a bell-shaped curve. If you just looked at that, you might say, well, that's a normal, because it's very close. So you want to kind of think of the t as sort of like a variation on a normal distribution. Okay, and we can graph it in a very similar way on the TI Nspire. And here it is on the TI Nspire. So you go in, put it F1. I'm up to F27. I've got several graphs going on at once here in different screens here, but put it one of your F's there and your functions, and it's just TPDF of x, comma 5. You can get that same place you get all your distributions, menu, probability, and then put it in. Choose it from there. Menu, probability, distributions, and then get it from there. Okay, so anyway, that's the graph of the PDF for that particular one. So let's graph the t distributions with 2, 5, and 15 degrees of freedom together in the same graph. You can leave the window the same as you had it before, and see if you could go ahead and graph these three and tell them apart, kind of compare and contrast them. Why don't you see if you could do this yourself now? Press pause. Well, if you did this, you're going to get all three of those graphed, and you can see that the graphs there are very similar. The Nspire graph's a little prettier, so let me go to it. So there's the graph on the TI Nspire, and as you can see from the formulas there, the three graphs have a TPDS with 1 degree of freedom, 3 degrees of freedom, and 5. So the brown one here, which is in the middle part, it's the lowest. In the outer part, it's the tallest. Shortest in the middle, tallest on the outside. Then if you go to 3, that's the blue one. That's the one's kind of in the middle here. Middle height in the middle, middle height on the ends. And the red one on the top is we have 5 degrees of freedom, tallest in the middle, shortest on the side. So by what we know already about this, we know that the area under all of these, total area, is 1. So the area is not changing. But what's happening is the spread is changing. And so we have a more spread, the smaller the standard deviation. The smaller the degrees of freedom. So the smaller degrees of freedom is actually a larger standard deviation. And so this one with 1 degree of freedom has more spread, okay? Whereas you have 3, it's a little bit less spread, and then 5 for the degrees of freedom is still less spread. So less and less spread as we change the degrees of freedom. Okay, we can graph a standard normal PDF along with a t distribution PDF with 3 degrees of freedom. Well, if you do that, then you can do the t PDF of x5, and I've made the darker one here, the normal PDF x01. So that number, the y1 is the standard normal, the y2, the thinner one, is the t PDF. Notice the t PDF is above the graph on the outside part, above the graph of the standard normal, but underneath on the inside part. It's a little easier to see with the Nspire here, and I've done several different ones here actually on the Nspire. Here's one with 1 degree of freedom. Here's one with 3 degrees of freedom. Okay, and then 5 degrees of freedom, and then 10 degrees of freedom. And you see that it's approaching the normal distribution. Okay, so if we graph a TCDF with 5 degrees of freedom, there's a built-in TCDF. I'm going to use negative 1,000 in place of negative infinity and 1,000 in place of infinity. Technically, these go all the way from negative infinity to infinity, in other words, all real numbers. But once you get past 1,000 either way, then you definitely have very little. In fact, 1,000 is probably quite a bit of overkill, but I can use that. So TPDF x5, TCDF negative 1,000 x5. So this will be the PDF and the CDF. And that Y3 I shouldn't have. That's a horizontal line I don't need. And so I have graphed this. Say there's the window I graphed it on. And you can see that there's the TCDF. Looks a lot like a normal CDF, of course, standard normal. And there's the TPDF down there. Here are both of them graphed together. A little bit better looking graph on a TI Nspire. Finer resolution and color. So the blue one down here that starts at it starts here at the x-axis. A horizontal asymptote here, increases up to an inflection point somewhere, concave up. Then it goes concave down, increasing, maximum right at 0. Comes back down, concave down, reaches an inflection point somewhere in here. Then decreases concave up with an asymptote of 0 on the right side for the PDF. The CDF, just like the normal, has an asymptote, horizontal asymptote of y equals 0 on the left, y equals 1 on the right. In between it's increasing, and right at the point 0.5 is where the inflection point occurs, just like it does on the standard normal. Okay, let's take a look at this. This is kind of cool thing that you can do in Nspire. You can actually create a slider, and this parameter df, for degrees of freedom, is controlled by the slider, and the red graph is now TPDF up to x, TPDF of x, with whatever that slider tells me is the degree of freedom. And so you can see this dynamically at work here. So if I see as I slide it from 1 up to 30, you can see how the graph changes. So notice as the degrees of freedom gets bigger, it gets less and less variable. Standard deviation is bigger than 1 in all these, but as the degrees of freedom gets bigger, the standard deviation is closer and closer to 1. Now for reference, I've also got the black graph, which is the normal PDF X01, which is a standard normal PDF. And you see, well, with degrees of freedom 1, they're a little different, but as we get that degrees of freedom bigger and bigger, it gets closer and closer. The TCPDF gets closer and closer to the normal PDF. Now, in fact, I'm going to go ahead and let's see, go to Control G. I'm going to take a look at what happens to the CDFs as well. So let's do a normal CDF of, let's see, I want to go from, well, we said negative 10 works instead of infinity, negative 10 x 01. So that's a standard normal PDF. Okay, and I need to change my window now. So now that's okay. I'm going to go up to 1.1. Take a look at that. All right, so there is our standard normal. Again, let's make it black. So in both cases, the black is the standard normal. And I'm going to graph a TCDF. Let's do that next. All right, so Control G will get me to where I can put in a graph. I'm going to graph the TCDF from, let's just go negative 1,000 to X. And degrees of freedom are going to be whatever DF is down here. Oops, did it? Let's try that again. TCDF negative 1000 to X with degrees of freedom, DF, enter, and there it is. So now notice that right now I've got degrees of freedom set as low as possible, which is 1. Okay, and that's the most variable you can make the graph, so it's the most spread, the largest standard deviation there, and you can see this spread out here. Still goes through, both of these CDFs go through 0.5 because why? Well, because on both these curves they're symmetric about the y-axis, so when you put in an x of 0.5, you know that, or x of 0, that the area under that curve is 0.5 to the left, or in other words, the y value up here on the CDF is 0.5 because the probability to the left is 0.5. Now look what happens to both the curves here. So as I increase the degrees of freedom, let's just scoot over just a little bit. So there's 2. Notice that the graphs in both cases are getting closer to their corresponding black graphs, which are the normal PDF and CDF respectively. So as I slide this across, you can see that in both the PDF and CDF case, as that degrees of freedom gets bigger and bigger, the graphs of the T's are getting closer and closer to the standard normal. Okay, so I think that goes over the basic characteristics of these. In the next video, we'll come back and do some probability and inverse probability calculations.